Imagine an AI that predicts the future multiple steps at a time and outsmarts the giants using a fraction of the computing power. Today, we are unpacking NVIDIA's wildly efficient Nemotron-3 Super. Welcome to our podcast, Artificial Intelligence, Papers and Concepts, curated by Dr. Satya Malik.
It's really great to be here today.
And before we dive into the deep end of the technical pool today, I want to quickly let you know that both of the hosts guiding you through this deep dive are entirely AI generated.
That's right.
But don't let that stop you from settling in, because the source material we have on the table today is absolutely incredible. We're digging into a highly detailed technical report from NVIDIA, and it outlines the architecture and training of their new 120 billion parameter model, Nemotron-3 Super.
It's a truly massive undertaking, this model.
It really is. Our mission for this deep dive is to cut through the heavy engineering jargon and help you understand exactly how this model achieves such massive efficiency. We're going to explore its unique hybrid architecture, and crucially, we're going to look at why it is specifically built for agentic reasoning.
Which is a huge shift.
Right, meaning it is designed to actually do things in the real world, like autonomously write software, test it, and use terminal commands. Okay, let's unpack this.
It is a remarkable piece of hardware-software co-design. Often when we look at new large language models, the conversation is dominated by, brute force scale.
Yeah.
Just throwing more and more parameters and compute at a problem until it gets smarter. But the approach with Nemotron-3 Super is entirely different.
How so?
Well, the engineering team looked at every single bottleneck in modern AI systems, from memory bandwidth to inference latency, and they designed a custom architecture specifically to bypass those physical limitations.
So I'm looking at these parameter counts in the report, and I have to admit I'm a bit confused by the math here.
Yeah, it can look a bit contradictory at first glance.
Right, because it says Nemotron-3 Super is a 120.6 billion parameter model. For you listeners who track these metrics, you know that is a massive footprint, yet the paper claims it's wildly efficient. How can a model that heavy physically be considered lightweight to run?
Well, the secret lies in the difference between total parameters and active parameters.
Active parameters.
Exactly. While the model has over 120 billion parameters sitting in its total architecture, it only utilizes about 12 billion of them during any single forward pass.
Just 12 billion? So it's mostly dormant.
Yes, exactly. A forward pass is simply one complete cycle of the neural network calculating and generating a single piece of text, or a token. So for any given word it generates, it's effectively only waking up about 10% of its neural pathways.
That makes a lot of sense. And before we get into how it pulls off that trick of only waking up 10% of its brain, I need to mention that this podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
It's a great service.
Absolutely. So getting back to this architecture, the report calls it a hybrid stack. What exactly are they blending together here?
They are interleaving two structurally different types of neural network blocks across an 88-layer architecture. The vast majority of the heavy lifting is being done by something called Mamba 2 blocks.
Mamba. I've seen that term thrown around a lot lately as an alternative to the standard transformer models we're used to.
Right, it's gaining a lot of traction.
But the paper uses some pretty heavy computer science jargon to describe it, saying it processes sequences in linear time with a constant size state. Can we translate that into plain English?
I can certainly break that down. Think about how a traditional transformer model uses self-attention.
The standard way.
Right. When it reads a long document, self-attention requires the model to compare every single new word against every single previous word it has already read.
Oh, so it's constantly looking back.
Exactly. If you're reading a massive code base, the memory required to hold all those comparisons grows exponentially. It becomes a massive computational bottleneck.
Got it.
Mamba 2, however, operates differently. Processing in linear time with a constant size state essentially means that instead of keeping every single previous page open on the desk to constantly refer back to, the model just takes a highly efficient running summary.
A state.
Yes, a state that never grows in physical size. It just updates its notes as it goes, which keeps the memory footprint completely flat, saving an immense amount of compute for long tasks.
That sounds incredibly efficient. But if Mamba is taking running nodes instead of keeping all the pages open, doesn't it run the risk of forgetting a highly specific detail from page 1 by the time it gets to page 1,000?
That's the main concern, yes.
But why not just use pure Mamba if it's so fast?
Well, you've hit on the exact reason why they built a hybrid. Pure Mamba can indeed struggle with perfect recall over massive context windows. To solve this, NVIDIA strategically interleaved a few traditional self-attention layers throughout those 88 Mamba layers.
Ah, so they mix them.
Exactly. You can think of these attention layers as global anchors. Periodically, these layers force the model to stop and look across the entire raw sequence to ensure it hasn't lost track of any long-range specific information, combining the speed of Mamba with the comprehensive recall of transformers.
That is a brilliant compromise. It keeps the fast-moving Mamba train on the tracks by occasionally forcing it to double-check its work against the original text.
Perfectly said.
But the hybrid attention mechanism doesn't explain how it's only using 10% of its parameters.
No, that's a separate innovation.
That brings us to the mixture of experts, or MOE, design. I love the analogy for this. Imagine a massive corporation with 512 highly specialized experts on staff.
Right.
If a problem arises, you don't call all 512 experts into a meeting room. That would be chaos.
And incredibly expensive.
Exactly. Instead, for any given problem, a router only calls in the top 22 experts who are best suited for that specific task. That's what Nemotron is doing for every single token.
What's fascinating here is that NVIDIA didn't just implement a standard mixture of experts architecture.
They changed it.
They introduced a novel concept called latent Mo. In a standard MOE model, even though you are only activating a few experts, you still have to physically move the data.
The tokens.
Right, the tokens, across the hardware to wherever those specific expert neural networks are located. This routing process creates a massive traffic jam.
Memory bottlenecks.
You hit memory bandwidth and communication bottlenecks on the GPU.
Right. It's like having a brilliant team of experts, but the hallways in the office building are too narrow. So everyone gets stuck in traffic just trying to get into the conference room.
That's a great way to put it.
But wait, the paper says latent Mo solves this by projecting the data into a smaller, compressed latent space before sending it to the experts.
Yeah.
If they are shrinking the data down to fit through the narrow hallways, don't they lose important nuances? How does the model stay accurate if it's operating on compressed data?
Well, the compression into a latent space isn't like indiscriminately cutting out pages of a report to make it lighter. It is a mathematical projection.
Okay.
Think of it like sending a highly optimized zip file instead of a massive folder of raw files. They project the token into a smaller dimensional space that preserves the essential semantic features of the data without the heavy computational bulk.
So the payload is smaller.
Because the data payload is now so much smaller, they can afford to drastically increase the total number of experts in the model up to 512 and increase the active experts per token to 22.
Wow.
They bypass the hardware traffic jam entirely, optimizing the model for both accuracy per computational operation and accuracy per parameter.
I see. So they shrink the physical data footprint to expand the actual brain power they can bring into the room. That is a very clever workaround.
It really is.
And speaking of changing how these models fundamentally operate, I really want to dig into how Nemotron actually generates text.
The multi-token prediction.
Yes. Because almost all models on the market operate autoregressively, meaning they just guess the next single word over and over again. But Nemotron-3 Super uses multi-token prediction. It is trained to predict multiple future words all at once.
If we connect this to the bigger picture, this is an absolute game changer for inference speed.
How so?
Well, traditionally, generating text one word at a time means the hardware is constantly waiting on the memory to load the next step. It's a bottleneck.
Like typing with one finger.
Exactly. By predicting multiple tokens simultaneously, Nemotron-3 Super is essentially creating an internal draft of its own future thoughts. It produces these candidate continuations and then verifies them using the main model in a single forward pass.
In one go.
Right. This mechanism is known as native speculative decoding. It drastically speeds up generation because the model doesn't have to pause, access memory, and recalculate from scratch for every individual word.
Here's where it gets really interesting, though. Standard multi-token prediction has a known flaw.
It does.
If you try to make the model draft too far ahead, the prediction heads start getting confused by their own generated text. It's like a writer getting so far ahead of their outline that they lose the plot entirely.
That's exactly what happens. The independent prediction heads become misaligned.
So how did NVIDIA manage to get this model to draft so far ahead without hallucinating or breaking down?
They implemented a shared weight innovation.
Shared weights.
Yes. In standard setups, you might have independent prediction heads, where one head only knows how to predict one step ahead, another only predicts 2 steps ahead, and so on. They become misaligned. NVIDIA created a unified prediction head exposed to multiple offsets and shared the weights across them.
Making it more stable.
This regularization process forces the head to be incredibly robust, even when it is dealing with its own self-generated hidden states during that auto-regressive drafting process.
And looking at the data, the results back this up completely. Because of this shared weight architecture, the model can look up to 7 steps ahead with remarkable stability.
7 steps is huge.
It actually beats highly respected models like DeepSeek R1 in acceptance rates. It is drafting its own thoughts, and the main model is accepting those drafts at a much higher rate.
Which translates directly to significantly lower latency and higher throughput for the end user. It turns a complex routing and generation problem into a highly elegant, fast solution.
Okay, so we have unpacked this incredibly efficient, hybrid, multi-predicting architecture.
The structural side of things.
Right, but an architecture is really only as good as the data you pump into it during pre-training.
Absolutely.
And the pre-training phase for Nemotron-3 Super is mind-boggling. They trained this model on 25 trillion tokens.
25 trillion.
But to do that without requiring the energy output of a small country, they used an ultra-low precision format called NVFP4.
This is where we get into the real dark arts of model training at scale. NVFP4 is a 4-bit floating point format.
4-bit? That sounds incredibly small.
It is. For context, historical models typically use 16-bit or even 32-bit precision to represent the billions of numbers that make up their neural networks.
So going down to 4 bits is a massive compression.
Shrinking the precision down to 4 bits saves an immense amount of memory and compute power.
Okay.
But it is inherently risky.
Because you lose detail.
Exactly. You are operating with far less mathematical fidelity. And the engineering team ran into a very specific, terrifying quirk during this run.
The zero-valued gradient panic. I can only imagine the sheer terror in that server room.
Oh, absolutely.
The engineers were monitoring the training run, and they noticed that a full 7% of the model's weight gradients just flatlined to absolute zero.
Right.
For you listeners, gradients are the mathematical signals that tell the neural network how to learn and adjust its weights. If 7% of those signals drop to zero, it usually means your multi-million-dollar training run is failing or getting stuck.
It looks like the model is just dying.
Exactly.
It's certainly presented as a catastrophic failure caused by the extreme low-precision format. But rather than scrapping the run, the researchers paused, investigated, and conducted an ablation study.
A side-by-side comparison.
Yes. They trained an identical, smaller version of the model in the traditional higher precision BF16 format and compared it directly against their NVFP4 model.
And what did that side-by-side comparison actually reveal?
They found that those zero-valued gradients weren't a sign of the model dying at all.
No.
The higher precision BF16 model had microscopic values in those exact same spots, numbers so infinitesimally small they are known as underflows. The low precision of the NVFP4 format was simply taking those microscopic underflows and rounding them down to zero. The ultra-compressed NVFP4 model was actually behaving identically to the fully mature higher precision model.
It was just truncating mathematical noise.
Exactly.
Wow, so they were panicking over nothing. The compressed model was just ignoring the dust. Once they proved that, they pushed forward, saving massive amounts of compute power without sacrificing any downstream accuracy.
It's a huge validation for doing extreme low precision training at scale.
So they finally get through this massive 25 trillion token pre-training phase.
The foundational phase.
Right. The model knows language, it knows facts, it has the raw intellectual capacity. But the second phase of training is what really sets this model apart.
The agentic phase.
Exactly. They focused entirely on making Nemotron-3 Super an agent. We know it's not just a conversational tool, but how did they actually teach it to take action?
They utilized a technique called software engineering reinforcement learning, or SWERL.
SWERL.
Right. Instead of just feeding the model a static data set of code and asking it to memorize syntax, they placed the AI inside isolated container environments using a system called Aptainer.
So they literally dropped it into a sandbox with a terminal and a broken code base.
Precisely. Using the OpenHands framework, they gave the model access to a terminal, a code editor, and real historical bug reports pulled directly from GitHub repositories.
That's incredible.
They essentially said, here is a broken piece of software, fix it.
So it had to figure it out on its own.
The model had to autonomously explore the code base, read the error logs, understand the issue, write a patch, and then run tests.
And the reinforcement learning part.
That aspect is critical here. The model was rewarded strictly based on whether its patch actually passed the objective ground truth tests in that sandbox.
That is true agentic behavior. It's trial and error. If it writes a bad piece of code, the test fails, it sees the error trace back, reads it, and has to rewrite the code until it succeeds. It is learning to program by actually doing the job of a software engineer.
Exactly. But they didn't just stop at coding. They also trained it heavily on conversational tool use.
Right. The goal was to make a highly competent agent that can look up databases, process returns, and handle complex requests. But as we know, you can't just download a massive, perfect data set of complex customer service interactions. How did they train it for that?
They built highly sophisticated synthetic data pipelines. Because real-world multi-step tool use data is scarce, they used other AI models to invent fake, highly detailed corporate policies and API documentations.
This part was so clever.
It really was. Then they generated hypothetical user personas with highly specific, convoluted problems.
Give me an example of how convoluted we are talking about here.
Imagine a simulated scenario where a customer wants to return a high-end laptop, but they lost the receipt. The item is slightly past the standard return window, and they want the refund issued to a different credit card.
A nightmare for customer service.
Absolutely. To teach Nemotron how to handle that, the synthetic pipeline sets up a multi-agent simulation. The AI models interact with each other, sometimes going back and forth up to 16 different times.
16 interactions.
Yes. Nemotron has to query the simulated CRM database, check the serial number, verify the policy exceptions, and execute the simulated refund API. It is synthesizing thousands of these complex scenarios to teach the model how to think on its feet, use tools correctly, and resolve multi-step problems without human intervention.
16 different multi-agent interactions just to teach it how to handle a complex return policy. That is an incredible way to generate training data. So what does this all mean?
When you step back and add it all up,
The Mamba attention hybrid architecture, the latent mode compression, the native speculative decoding predicting 7 steps ahead, the ultra-low precision NVFP4 training, and this intense sandbox-based agentic reinforcement learning road.
right, when you put that together, the final performance metrics are staggering. Nemotron-3 Super is capable of handling context lengths up to 1 million tokens.
1 million.
Yes. To put that in perspective, you could feed it a dozen massive textbooks or an entire enterprise-level code base all at once, and its hybrid architecture ensures it won't lose track of the detail.
That's impressive.
And when you compare it to giant open-weight models in its class, specifically GPT-OSS 120B and Qwen 3.512D2B, Nemotron matches or beats them in accuracy across the board.
But here's the real kicker.
Because of all the architectural optimizations we discussed, it achieves up to 2.2 times higher inference throughput than the GPT model, at an incredible 7.5 times higher throughput than the Qwen model.
7.5 times faster. That is not just a small incremental optimization.
No, it's not.
That is a fundamental paradigm shift in how efficiently we can run models of this massive scale.
It absolutely is.
And for you listening, this is exactly why this deep dive matters. We are rapidly moving past the era where AI is just a neat tool that drafts emails or answers trivia questions.
Right.
What NVIDIA has documented here with Nemotron-3 Super is a concrete blueprint for highly efficient, highly capable AI agents. These are systems explicitly built to execute complex, multi-step tasks, navigate operating systems, and autonomously debug software.
All without requiring a multi-billion-dollar supercomputing cluster to run efficiently.
Exactly. It brings true agentic problem solving out of the research lab and much closer to everyday practical application.
This raises an important question. If this model was trained by being placed in an isolated sandbox to test its own code and learn from its own real-world failures, how far are we from a future where AI models independently invent, test, and verify their own entirely new software architectures while we sleep?
That is a fascinating and slightly intimidating thought to leave off on. And that brings us to the end of today's exploration. Thank you so much for joining us for this deep dive into the architecture and agentic training of Nemotron-3 Super. If you want to keep exploring the absolute cutting edge of artificial intelligence with us, please make sure to subscribe. Until next time, keep questioning, keep learning, and we'll see you on the next deep dive.